Hi, welcome back to Pushing Voxels Forward. This is episode 6. As mentioned in the last episode, I was optimizing the code and figured I'd take you guys along with me. And I ran a profiler real quick, observed it, and noticed something really weird. The assert statement here is taking up 5.7% of the total runtime, and we're in release, and I saw that and I thought to myself, and I was like, wait a minute, why is an assert statement getting compiled in the release build? And then I removed it, and then something even stranger happened. The execution time of the program went from, or at least the extraction went from 1900 milliseconds to 1970 milliseconds. So for some reason, having this assert statement here is making the program actually faster, which makes no sense to me, especially considering this line is exactly the same as the following line. And I had to take a look at it just to make sure that it was actually getting compiled and something weird wasn't happening. So here's the disassembly for it, debugging. It's actually being compiled here. And then the following line, it looks like it's just taking the value here. If I had to guess, unfortunately, I'm not really good with assembly, at least on the x86 platform or whatever this is. I assume it's x86, but I could kind of see the basics. So we're gonna try to figure out what's going on here. Alright, so just to get some times out there, I went ahead and ran the program. Right now it completes in 1861 milliseconds. I'm going to go ahead and comment out the assert line, and then I'm going to pause the recording real quick. Alright, went ahead and commented out and reran it, again with the recording paused just so we get accurate timings. And as you can see, completed in 1927 milliseconds. So it is slower. I'm not just making this up. The first thing I want to do though is move this statement up here and then see what kinds of results we get. Alright, well, give or take, it's more what I expected. We're at 1880, so it is down and close to what it was originally, and this is with assert below it. So what that means, if we uncomment and then run it again, we're going to get those same slower speeds. And that is exactly the case that we see here. It is slower. I really have no idea what's going on, but I'm going to go ahead and just debug it here real quick, and then we're going to take a look at the disassembly. So we go to debug, and then Windows. Oh, actually I have it open here. And because I don't know how to have two disassemblies open at the same time, I have paint.net open right here. And so we can kind of see the side by side of what it would look like. Well, I've been looking at this for a while. I have the disassembly of the full function for with and without the assert statement, and for some reason the function is entirely different. I honestly have no idea what's going on. Right off the bat, when I switch between the two, it looks similar enough, but for some reason, as you can see right here, it's using a different register than it is right here, and it does that throughout the function. And if we actually scroll down a little bit and then switch between the two, we can start to notice bigger changes. So with the assert statement, as you would expect, when it creates the next index and assigns it to 0, this XOR statement right here is setting it to 0 because anything exclusively ORed by itself is 0, and then storing it into here, I guess, but that's actually not present here. For some reason, it looks like it's setting next index to 0 inside the loop, which really doesn't make a whole lot of sense. And then also there's all of this code right here that's being executed outside of the loop as well with the assert statement, which makes sense because this isn't stuff that should be executed within the loop every time. So I really have no idea what's going on. And unfortunately, my expertise doesn't lie within the disassembly and then getting it to that level of optimization. So maybe we'll have to leave the assert statement in there, which would be stupid, or figure out what's causing that so we can trigger the compiler to properly make that optimization. Alright, I have good news and I have bad news. The bad news is I couldn't figure out really what's going on, why assert happened to be faster. The good news is I, in release build, just enabled the end debug flag, which is how you cancel out assertions in release, or really just cancel out assertions at all. and then we actually get significantly faster speeds. It went down to about 1812 milliseconds on average versus the 1956 that we were getting, so that's huge. Also, taking a look at the disassembly here for real, I noticed, well, first off, I figured out that this stuff that's going on here is pretty much the same as what's going on in the assert, although there is an extra instruction here, LEA. I'm not really sure what that does, but for the most part, the code after that is the same. But I noticed here that there's probably some fetch here. I'm not sure, again, what moveZX is, but it's some sort of move register, and it's fetching the lookup table. So I want to go ahead and try switching back to the multiplier, why did I say it like that? Multiplier, and see if it looks any different. I also have another optimization in mind just looking at this. So then we go to the disassembly. Wow. Okay, so yeah, it definitely went down, and that noise that you just heard was my dog. I thought I would share this with you guys real quick. For some reason, when I changed it to times multiplier, because I forgot to uncomment this line here, my display driver crashes, and I mess with it for a little while, and then I realize it's creating 31 million triangles. So maybe that has something to do with it. Alright, so there was an unfortunate false alarm earlier. I said that this went down significantly, but it's because I had that times multiplier, or multiplier times equals 3 commented out, so the compiler saw that there was actually no code really being executed there. So that's unfortunate. So I went ahead and reran the profiler, and I can see that this line is actually a really expensive line, and the optimization that I was talking about earlier was only adding to that when we know that V is not 0. So we could probably do something like this. Not 0. And then see if we get anything better, because obviously if it's not 0, then we don't have to, I'm sorry, if it is 0, we don't have to do the multiplication here. Well, unfortunately, that didn't result in any improvements. The time went up, so time to try something different. Instead of doing that, what we're going to go ahead and do is do something like this, and then only write to the mask, write to the cells mask after all this. Right, because that might actually be a little bit faster than that. We'll see though. Alright, went ahead and did that, and as we can see here, on initial execution it's down to 1781, and then re-execution 1765, so that's down almost 40 milliseconds, which is significant. So I'm going to go ahead and look at this, experiment with a couple things, and then see if I can get it to be even faster doing stuff like that. Alright, I managed to find another optimization. We're down to, on a rerun, 1709 milliseconds. You'll see there, if you pay close attention, that there was one that's over 4 seconds. That's because, I might have mentioned it before, but my CPU sometimes has throttling issues. I'm not really sure why. But what I did was, there were 3 times in this function where these values were looked up, and instead of keep looking them up, I just decided to pull them out, which made the most sense. And what I'm going to go ahead and try to do now is switch the order here, because the table DZ comes last, so I wonder if that would cause a performance or a cache miss. So that didn't really make much of a difference. It decreased a little bit, but not really by much. So what I decided to do was decrease or get rid of lookup tables altogether, and decided to go with just math, because we could do that too. And the performance actually tanked. It went to about 750 milliseconds on a re-extract on average, so that was slower. What I want to go ahead and try to do next is actually compress this, so instead of full 32-bit integers, it actually compresses into single bits, and that way we can just fetch one lookup and have it be in a full cache line for the whole thing. So as many of you probably predicted, I went ahead and did that. I created a mask which represents all of these bits here, and then looked up that mask, and it's significantly slower. It's about 1850 on average for a re-extract. So most of the time these kinds of optimizations don't work. It's best to have a lookup table when you can, especially in a critical loop like this, because the compiler is probably going to optimize it the best that it can. But you know, of course, it never hurts to try, especially if you can get performance in a tight loop like this. Just for the heck of it, I went ahead and tried something like this, where we compress the table into a single lookup, and for some reason that's actually slower. It's about 50 milliseconds slower than the fastest that we had it. Multiplying, again, if you're going to be doing arithmetic math like this, probably going to be slower than just using a regular lookup table. Alright, there it is. Our first under 1700 millisecond re-extract. Didn't really change much, but what I did do was I reprofiled it, saw that a lot of the calculations were going into this, and then just changed everything to be unsigned, because we were working primarily with the unsigned stuff, and I just have the funny feeling that multiplying unsigned by signed stuff is going to cause some issues, possibly even casting cost. So I did that and then managed to squeeze a little bit more performance out of it. For the first time in benchmarking, I changed it to use Morton coding, and we actually get faster results. I got it down to 1676 being the lowest, so on average maybe between the 1691 and that, maybe 1680, give or take. So that's actually really surprising, because I haven't actually seen Morton coding be faster before. Oh man, look at that time save. We broke the 1600, guys, down to 1575 on a re-extract. What I did was, when I was profiling, I noticed that one of the most expensive lines was the calculating edge crossing, and I took a look at it, and I noticed that it's actually sampling the grid sign at the same point 3 times for every edge. So that's an obvious optimization right there. So I took that out. So we're only calculating it once, and that's how we're able to get that massive time save. And actually, this optimization should be working, should actually work in the regular marching cubes too. So I'm going to go ahead and enable that and see what kinds of speeds we get, because that was one of the big bottlenecks of that as well. Oh yeah, with regular marching cubes we're down to 1124 and 1136, so 1130 on average for a full extraction. So that's really awesome, really nice optimization there. I'm really glad to have found that. Alright everyone, well that's going to have to do it for this episode. I hope you enjoyed watching me kind of fumble through the disassembly and optimizing process and learned a lot. We shaved a lot of time off. I honestly didn't expect to get it down this low, especially because I think the authors of the SnapMC paper said that it took twice as long for their marching cubes implementation, and my speeds run roughly at the same as theirs when theirs is multi-threaded. So really happy with this. I probably will optimize it a little bit more off camera, and there's also a bug that I have to fix. As you can see, there are more vertices than there are primitives. That's actually kind of a simple fix. I just haven't gotten around to doing it. But as always, be sure to check out voxelspace.net if you haven't. Thank you all for watching, and I'll see you next time.